This video is on the 3D KSP and common ion effect notes part 2. I'll talk about what the common ion effect is and work through example number 3. The common ion effect is one in which we look at the solubility of a salt in a solution containing another salt having a similar ion. It's an application of Le Chatelier's principle. Let me give you an example of what I mean. Here's an image that shows you some silver acetate. It's a slightly soluble salt in a saturated solution. So here you see the silver acetate as a solid, and here's the ions floating around. There's also some nitrate ions in there as well that aren't actually pictured in the diagram. But you can see on a macroscopic level the silver acetate precipitating out. If we had put this same salt in a solution containing silver nitrate, there would be more silver ions in the solution, and they would actually cause this silver acetate to be less soluble and to precipitate out. Here's another way of looking at it. If I write down the dissociation equation for silver acetate, it would look something like this. Got some silver ions and some acetate ions. If I add silver nitrate to this solution, essentially what I'm doing is increasing the concentration of the silver ions, which would then shift the equilibrium towards the reactants, towards this solid, and you would get the silver acetate precipitating out. Some people call this process salting out, where if they want to remove a particular salt from a solution, they can actually add a common ion, and that'll cause that salt to precipitate out. In example number 3, you'll work with a problem where you're given the KSP and a solution containing a common ion to the solute, and your job is to calculate the molar solubility, or the solubility in grams per liter. These are the steps you'll take to solve the problem, and here's the problem we'll solve. What is the solubility in grams per liter of calcium fluoride in a 0.01 molar calcium nitrate solution at 25 degrees Celsius? The first thing you'll do is write out the dissociation equation for calcium fluoride and water. So we've got calcium fluoride as a solid in equilibrium with its ions, calcium and 2 fluoride ions. Write out the KSP expression. So the KSP will equal to the concentration of the calcium ions times the concentration of the fluoride ions, quantity squared. Next, you should look up the KSP value at 25 degrees Celsius in the Handbook of Chemistry and Physics, and I have a link to it here for calcium fluoride. So when you click on that link, look at calcium fluoride's KSP, you will see that it is 3.45 times 10 to the negative 11th. Now I don't know what the concentration of the calcium ions are, so I will call them X. But I do know that I'm putting this calcium fluoride in a solution that already contains some calcium ions. It contains 0.01 molar calcium nitrate. Let's take a look at calcium nitrate, which is a very soluble salt. So it completely dissolves when you put it into water. Any nitrate will be very, very soluble. That means that if the concentration of the calcium nitrate is 0.01 molar, that because the calcium nitrate is in a 1-to-1 ratio with its calcium ion, the concentration of calcium ions in that solution will be 0.01 molar. So what that means is when we're writing the KSP expression, we're going to gain calcium ions not only from the calcium fluoride, but from the calcium nitrate that's already there. So we'll say plus 0.010. Now that is your common ion right there. And then we have to multiply that by the concentration of the fluoride, which we'll call 2x, because that concentration of the fluoride ions will be twice the calcium. And then we've got to square that. Essentially what we'll do here is just solve for x. But we're going to simplify our math a little bit here by making an assumption. We're going to assume that the calcium ions from this slightly soluble salt will be negligible compared to the calcium ions that we have from the calcium nitrate. So this x is going to barely make a dent, and we'll just bring it to 0. We're allowed to make that shortcut when X is within 5% of the common ion concentration. So if we solve for this X value, and that X value is within 5% of 0.01, that would be, 5% of that would be 5 times 10 to the negative 4th molar. As long as X is less than that, we're okay making this assumption. So let's just see if it is. So this simplifies to 0.010 times the quantity 4x squared. So that gives us 3.45 times 10 to the negative 11th is equal to 0.040 x squared. And I'm going to divide both sides by 0.04. So that gives me 8.625 times 10 to the negative 10th is equal to x squared. I'll take the square root of both sides. So x is equal to 2.9368 times 10 to the negative 5th moles of calcium fluoride per liter. Now that number right there, that x value, is definitely less than 5 times 10 to the negative 4th. And so we're good to go. If it hadn't been, we would have gone back here, we would have kept the x in and just done a little bit more math. It's not hard, it just takes a little bit more time. Now, I want my answer in grams per liter, so I will multiply this by the molar mass of calcium fluoride, which is 78.08 grams. And that gives me an answer, which I'll round to 2 significant digits because I just have 2 significant digits here, of 0.0023 grams of calcium fluoride per liter. Now that will, I think what we want to do is compare that answer to when we didn't have the common ion at all, which is what we did when we did the example number 2. So I'll just show you what that value was. Without that common ion, the solubility of calcium fluoride was 0.016 grams per liter. But with that common ion, it's now down to 0.0023. It's much less soluble with the common ion there. And that, my friends, is the common ion effect. And that's it.